So what I'm going to talk about in this video, right, is determining the probability of finding an electron in a 2D particle in a box, right, that's a square. So we have both sides are going to be equal to each other, and, we're going to have in the x direction, right, the principal quantum number is going to be equal to 2, and we're going to be looking at the 0 to L over 2 region for that dimension, and then for the y dimension, right, principal quantum number is going to be equal to 3, and we're going to be looking at that dimension from the perspective of 0 to L over 3 in that case. So first things first, right, what we're probably can do is we can just simply, qualitatively assess what it's going to be by just simply, plotting out what this wave function is going to look like, this 2D wave function. So if we write out, right, what the wave function is the wave function is in regards to nx and ny, right, where both of those are the quantum numbers of the two different directions. And so you have the square root of 2 over Lx times the sine of nx times pi times x over Lx, right, where nx is the principal quantum number in the x direction, right? X is just simply the position in the x direction, and Lx is the length of the x direction. That's going to then be multiplied by the square root of 2 over Ly times the sine of ny times pi times y over Ly, right? And so as you can see right here, right, so this is just simply two individual 1D particle in a box equations multiplied by each other, right? Where the only difference is that they can have different lengths and they can have different quantum numbers, right? But you multiply them together, right? And then you get the overall wave function for this 2D particle in a box model. And so if we were to plot this and look at it, right, it's just simply a square. In this case, right, so we have nx is equal to 2 and ny is equal to 3. So if we're looking at this right here, right, so if nx is equal to 2, that tells us that we have one node in the x direction, right? So we can just simply plot that right here. And then for ny, right, we know that we have two nodes, and those are going to be then at the L over 3 and then the 2L over 3 positions, right? Because if this is L and this is L, right, this is going to be L over 2, this is going to be then L over 3, and this is then the 2L over 3 right here. So if we were to plot this out, right, you just simply have your topographical map as your easy way to do it, right, in terms of like alternating what is a hill and what is a valley. And so what we're looking at, right, is in the x direction from 0 to L over 2, right, so that's this space right here. And then from the, I jumped to the wrong problem. Right, we're looking at from the in the x direction, right, from 0 to L over 2, which is this space right here. And then in the y direction, we're going from 0 to L over 3, which is this space right here, right? So we're looking at essentially this quadrant right here. And so just qualitatively looking at it, we can tell that we're only at a sixth of the space, right? So we're only at a sixth of the total space of the box. And so we would expect the probability to really just be, a sixth of the time we'd expect to find the electron in that space right there. And we can just simply do that again by looking at it and breaking out, where the peaks are or where the nodes are, right, of everything, and then just simply taking all of that into account to determine what it is. And we can do that again, qualitatively just by looking at it. If we want to put more, rigor towards it, I guess you could say, and qualitatively assess it, we'd have to use calculus, right? So we'd have to integrate over those two different directions, and we'd have to, integrate both the x and the y components in those cases. And so if we do the probability, right, so the probability is just simply the wave function squared, so nx and y, right? So what we get then is 2 over Lx times the sine squared of nx times pi times x over Lx times 2 over Ly times the sine squared, of ny times pi times y over Ly. Right, so if we just simply integrate that, and I'm going to, right now, I'm just going to go ahead and say it, right? I'm going to skip a step right? Because typically when you do the integration, right, you have the one part minus the other part. If you're, integrating over a region, I already know off the top of my head, based off of previous ones that I've already done, is that when L is equal to 0, it's going to be equal to 0 for that whole part right there, right? So the only part that I actually have to worry about in the integration math is actually the Lx is equal to L over 2 and the Ly is equal to L over 3 region in those cases. And so so if we go ahead, right, and we do the integration, and what we get then is 2 over L times x position, or sorry, it's 2 over Lx times the x position over 2 minus Lx times the sine of 2 pi nx times x over Lx over 4 pi nx times 2 over Ly times y over 2 minus Ly times the sine of 2 pi ny times y over Ly over 4 pi ny. Right, so that right there is just simply the equation that we have. Now we can just simply plug in the values that we need in these cases, right? So we have 2 over Lx times, right? And so now the x position that we're looking at is L over 2. So we plug that in, right? So L over 2 minus Lx times sine times 2 pi times, right? And so the nx value is equal to 2. So we have 2 times the x value, which is L over 2 over Lx. And that's all within the sine. And then that's all over then 4 pi times 2. And then we have the y part. So that's 2 over Ly times L over 3. Right? So y position is L over 3 now. Over 2 minus Ly times sine of 2 pi times, now the ny position, right, or sorry, the principal quantum number for the y direction is going to be 3 in this case, times the y position, right, is going to be L over 3 over Ly, and all of that then is going to be over 4 pi times 3. Now, if we go through, right, and we evaluate everything for ourselves, right, we're going to still have the 2 over Lx for right now. So then we have Lx over 2, and it's Lx and this is Ly. Right, we're going to have Lx over 2, so that comes out to being Lx, oh, sorry. It's going to come out to being Lx over 4 minus, and so if we're going right here, right, and we're looking at, and we're evaluating out this, this sine portion of the equation, right? The Lx and the Lx cancel out, the 2 and the 2 cancel out. But one thing we know, right? The sine of 2 pi, right? The sine of any integral of pi is going to be equal to 0. So this whole thing comes out to being equal to 0, which is very easy and nice for us. So that's equal to 0. And so the next, right, we have 2 over Ly times, so now, right, we have Ly over 3 over 2, so that ends up being equal to Ly over 6. Minus, right, and so now again evaluating all of this, right, so the Ly cancels, the 3 cancels, sine of 2 pi is equal to 0, so this whole thing comes out to being equal to 0, so minus 0. So if we clean this up a little bit, right, we have 2 over Lx times Lx over 4 times 2 over Ly times Ly over 6. So we can see that the Lx's are going to cancel out. We can see that the Ly's are going to cancel out. So what we get then is 2 times 2, which is 4. And then we have 4 times 6, which is 24, right? And so if we simplify that down, we get 1 over 6, which is what we got when we were qualitatively looking at it as well, right? But we were able to mathematically now prove that the probability of finding that electron in that region with those principal quantum numbers is going to be, a sixth of the time.